This is the fifth lecture of this series, EPR to quantum communication. Please go through my previous lectures on EPR paradox, quantum entanglement, Bell's theorem and quantum teleportation. In this lecture, we will talk about quantum cryptography. Quantum cryptography by itself is a vast field and people are still doing research in this. And these are some important references. These are some important references on quantum cryptography which are listed over here. And the first one is this by Bennett Brassard in this Proceedings of IEEE International Conference on Computer Systems and Signal Processing, Bangalore, 1984. So the BB84 protocol actually was discussed in this conference. And then by Bennett, again another important paper, Quantum Cryptography using any two non-orthogonal states, published in Physical Review Letter, volume 68 3121, 1992. And this paper is also important by Arthur Eckert using the EPR entangled state, this cryptography using this EPR entangled state. Arthur Eckert, quantum cryptography based on Bell's theorem, PRL 67. Bennett, Brassard, N.D. Mermin, quantum cryptography without Bell's theorem, published in Physical Review Letter, 68 volume 557, article number 1992. Bennett, Brassard, Eckert, quantum cryptography, Scientific American, 267 volume, page 50, 1992. And these three review paper also are very important references for this topic, this quantum cryptography. So these are these three a very good review one can have from these review papers by Nicholas G. Sin et al. Quantum Cryptography Reviews of Modern Physics, volume 74, page 145, 2002, and this review paper by V. Scarani et al. The Security of Practical Quantum Key Distribution, Reviews of Modern Physics, volume 81, page 1301, 2009, and the last one is by J.W. Pan et al. Secure Quantum Key Distribution with Realistic Devices, Reviews of Modern Physics, volume 92, page or article number 025002, 2020. I should also mention here some recent landmark accomplishments of quantum cryptography experiments. The first one, for example, by J.W. Pan et al. Satellite to ground quantum key distribution, published in Nature, volume 549, page 43, 2017. Second one I should mention about this paper, Liao et al. Satellite relayed intercontinental quantum network, published in Physical Review Letter, volume 120, page 030501, 2018. And by this Chinese group, JW Pan et al. An integrated space to ground quantum communication network over 4,600 km, published in Nature, volume 589, page 214, 2021. Quantum cryptography provides secure communication for sensitive information such as military communications, financial transactions, personal data protection, etc. And this communication method utilizes the principles of quantum mechanics to provide secure communication, and that's why we call it quantum communication. Before we go to quantum cryptography, here we discuss classical cryptography through which one can exchange secret messages with others. The history of secret communication appears in Chronicles of the War between the Persians and the Greeks in the 5th century BC. In history, particularly during wars, secret messaging has often determined life and death, victory or defeat. A famous example of how the security issue of cryptography has influenced the outcome of a war is how the British, with the help of Alan Turing, cracked the Enigma code used by the Germans to communicate during Second World War. So let us now talk about a very simple cryptography scheme known as Caesar cipher, which is named after Julius Caesar, who used it for military correspondence. The idea is very simple. Every letter of the normal alphabet is shifted by a certain number of letters. For example, the plain alphabet used to write the original message, this is the original alphabet as we all know, and now in the encrypted alphabet, every letter was actually shifted by one letter forward. So take for example, in the encrypted alphabet, every letter is shifted by one letter forward. So one can of course shift 2 letters or 3 letters in the encrypted alphabet. as well. Okay, so in the encrypted alphabet we take the letters as it starts with B. So in place of if in the original message there is a letter A, in the encrypted message we will replace this A by B, and B by C, and C by D, and we will replace D by E, E by F, we will replace F by G, G by H, I by J, J by K, K by L, L by M, M by N, N by O, P, P by Q, Q by R, R by S, S by T, E by U, U by V, V by W, X, Y, Z, and then A again. Okay, so this is the encrypted alphabet. So this is the original alphabet. This is the original alphabet, and this is the encrypted alphabet. So this is the encrypted alphabet. Encrypted alphabet. So now in this encrypted alphabet, what we have done, we have actually every letter is shifted by one letter forward. So as I mentioned that one can of course shift 2 letters or 3 letters also in the encrypted alphabet as well, or make a hybrid shift also. Okay, so for this protocol the secret key of the encryption is, so what is the secret key of this encryption? Secret key for this protocol is shifting of one letter forward. Okay, so now suppose we want to send a message, say for example, meet me at the park, to someone, but we do not want anyone else to be able to read that message, and we can encrypt the message using this encrypted alphabet. So let us write down the original message and the encrypted message using this encrypted alphabet. Okay, so that's what we will do. So the original message, we want to send this original message. Let me write it here. This is the original message, meet me at the park. Okay, so this is the original message, and using this encrypted alphabet, what will be the encrypted message? That is, I am writing it here, encrypted message. So we are encrypting it, we will encrypt this message using this encrypted alphabet, and so that no one can. So we will encrypt this message using this encrypted alphabet, because we do not want anyone else to be able to read this message. Okay, so now in place of M we will write N, right? So here, and E will be replaced by F. Because of this encrypted alphabet. So F, again E, in place of U will write F, and in place of T we have to write U. So this meet becomes NFFU, me. So M will be replaced by N, E will be replaced by F again, at A will be replaced by B, T will be replaced by U, here also T will be replaced by U, H will be replaced by I, and E will be replaced by F, P will be replaced by Q, A will be replaced by B, and R will be replaced by S, K will be replaced by L. So this is the encrypted message which one can send from the receiver to the sender by some person, and in the middle, if anyone want to know the message, actually he or she should know the encryption. What is the encryption? That means that this is done, the encryption is done in this way, that shifting one letter forward actually is done for this to create this encrypted alphabet, and this is the encrypted message. And when the receiver will receive this message, what he will do, he will actually make a backward shift of the letters. He will make a backward shift of the letters to reveal the original message, that is meet me at the park. Now this is a very trivial kind of encoding of a message and is also not very secure. So one can easily crack this encryption to reveal the original message by a careful analysis of English alphabet. Let us discuss another example of classical encryption or classical cryptography. Suppose Alice wants to send a binary secret message to Bob. So Alice wants to send a binary secret message to Bob, and Bob is at a far distance from Alice. Suppose Alice wants to send a binary secret message to Bob, who is at a distance from Alice, and the binary message is as follows. So the binary message Alice wants to send to Bob is this one, 0 1 0 1 0 0 1 1 0 1. So this is a binary message. We all know that information can be stored using the binary digits 0 and 1. So this is the original message which Alice wants to send it to Bob, who is at a distance, but Alice will use this cryptography using a secret key. Since Alice want to send this message secretly to Bob, what she will do, Alice using a secret key, Alice will first encrypt this message, that is the encryption part of the cryptography. Okay, that is the encryption part of the cryptography. What Alice will do, Alice will use a secret key. So using a secret key, Alice will first encrypt this message. So this is the original message. Let me write it down again: 0 1 0 1 0 0 1 1 0 1, and there is a secret key which Alice and Bob, only they know about the secret key. So secret key is, so this is the message, right, original message, and the secret key. So remember that Alice want to encrypt this message using this secret key. Secret key is as, so using a secret key, Alice will first encrypt this message, and then that encrypted message, what Alice will do, Alice will send that encrypted message to Bob, and since Bob knows since Bob also have access to that secret key, then he can decrypt the message again. So the secret key is as follows: 1 0 0 1 1 0 1 0 1 0. So what Alice will do, Alice will use this addition modulo 2. Using these two binary digits, Alice will encrypt the message. Alice encrypts this is the original message. Using this secret key, she will actually encrypt the message using addition modulo 2. So she will use this addition modulo 2. So this is basically, if we remember we can recollect the XOR operation. We recollect the XOR operation, logic gate operation for binary digits. So Alice encrypts the message by addition modulo 2, which is just the XOR gate operation. So we can recollect the XOR logic gate operation for binary digit. Alice has this original message encoded in this binary string, and this is the original message. This is the secret key, which is again another binary string, and Alice will actually encrypt the message using this secret key. So this is the secret key over here. We do this addition modulo 2 here. So we can recollect the XOR logic gate operation for binary digits. So 1, and this is 0. So this will be 1 1 0, this will be 1, it is 1 and 0, this is again 1, and 1 plus 1 in the addition modulo 2 becomes 0, and 0 plus 0 is 0, 1 0, so this will be 1 1 1, this will be 0 0 0 0 1 0 1, and this will be 1 and 0, so this will be 1. So this becomes the encrypted message. This is the encrypted message. This string bit string becomes the encrypted message. Alice will actually send this encrypted message to Bob. So Alice will actually send this encrypted message 1 1 0 0 1 0 0 1 1 1. Okay, so you can see that this is the original message, and this is the encrypted message sent by Alice to Bob. And Alice used actually what she used? She used a secret key, and she has done this addition modulo 2 or the XOR operation with these two bit strings, and while doing that she actually got this encrypted message in this way, and she sent this encrypted message to Bob. Now what Bob will do, so with this encrypted message, what Bob will do, because Bob has access to the secret key, so this secret key also, so this secret key is also there with Bob, this 1 0 0 1 1. So 1 0 0 1 1 0 1 0 1 0. So this is the encrypted message, and this is secret key. This is the secret key. So what Bob will do again this addition modulo 2. That means this XOR operation, gate operation, XOR logical gate operation, he will apply it here also, like addition modulo 2. So if he does that what he will obtain 1 0 will be 1, 1 1 will be 0, 1 0 will be 1, 1 0, 1 0 0 will be 0, 1 1 is 0, 1 0 1, 0 0 0, 1 0 1 and 1 1 0. Okay, so we can see that in this way actually Bob can reveal the original message. So this is the original message. Now, so using this secret key, Bob decrypts the message by this addition modulo 2a again. So we can easily see that this was the original message here, 0101 001101. So he can actually reveal the original message if he has the access to the secret key. Classical cryptography has evolved through history, and there have been attempts to crack the encryption, leading to new and more secure encryption techniques. But all these encryption codes or whatever have in common is that they can in principle be cracked and hence not secure. A popular public key crypto system, namely this RSA, this is a popular public key crypto system. This is a popular public key crypto system, that is, this RSA is widely used for secure data transmission. The security of RSA relies on the practical difficulty of factoring the product of two large prime numbers. However, advances in quantum computation, particularly with the implementation of Shor's algorithm, threaten the RSA security. The classical cryptography scheme I have discussed over here is also not safe and secure. For instance, Alice here actually encrypts her message by this secret key, and this secret key Alice has to communicate to Bob, right? Otherwise Bob cannot decrypt the message. So Alice communicates this secret key to Bob via a phone call or another classical channel, and after that she sent the encrypted message to Bob, right? So now any private classical channel can be monitored by a third party, or eavesdropping can take place without the knowledge of Alice and Bob. So this is a challenge. So the challenge is to securely generate a secret key between Alice and Bob, who are separated by long distance. So what is the challenge? The challenge is to generate this secret key even if Alice and Bob, they are at far away from each other, and at a distance they can actually generate how to generate this secret key when Alice and Bob are far away from each other, and that should be secure also. So at this point quantum cryptography offers a solution. So let us now discuss the simplest secret key generation protocol or quantum key distribution protocol known as BB84 protocol. So this is a quantum cryptographic protocol which is known as BB84 protocol or quantum key distribution protocol. Sometimes we write it as QKD, which is the short form of quantum key distribution. So this protocol was proposed by Bennett and Brassard in 1984, and this quantum cryptography protocol works as follows. So basically Alice and Bob, they are at a distance, they are far from each other, Alice and Bob. So the purpose is to generate a secret key between them when they are at a distance. So earlier we have shown that Alice can use the secret key to encrypt her message and then send it to Bob, and Bob will then decrypt the message using the same secret key. So now here the purpose is to generate that secret key when Alice and Bob are at a far distance, and here quantum mechanics will help, quantum physics will help them to generate the secret key which is more secure. The security will be ensured by quantum mechanical principle. So here Alice and Bob will generate the secret key at a distance, where they are at a distance, and that secret key will be secured by the principle of quantum mechanics. So let me go into the details of this BB84 protocol, that is the quantum key distribution protocol, step by step. In step 1, Alice will use qubits to encode binary information 0 and 1. So instead of classical bits, what Alice will use, she will use qubits or quantum bits to encode this binary information of that secret key, the secret key that Alice and Bob actually want to generate at a distance. So Alice will use qubits to encode this binary information. and these qubits can be realized say for example by spin half particles. Qubits can be realized using this spin half system, or they can use photons. So most of the quantum cryptographic experiments are done with photons. Photons are easy for transmission. So photons with different polarization state. So these qubits can be realized say for example by using this spin half system or spin half particles, or by photons with different polarization states, horizontal or vertical state. We write it in this way, horizontal state or vertical state on the depending on this their photon polarization. Here for simplicity, let's say Alice picks up spin half systems, because from the beginning we have considered spin half system, so it will be easy to understand if we actually describe everything in terms of spin half system. Mathematically, when we consider this horizontal and vertical polarization of photon, the physics and mathematics are the same, because both of them are two-level system. So let us stick to the spin half system, and what Alice will do, Alice will prepare a series of qubits in one of the four possible states. For simplicity, let's say Alice picks up these spin half particles and prepares them in one of the four possible states, state like this: spin up along z axis, spin down along z axis, spin up along x, and spin down along x. So these are the four possible states. Alice actually prepare the particles, spin up particles in one of, Alice prepares a series of qubits in one of these four possible states. So basically these two states are the eigenstates of this sigma z operator. We have already explained in our earlier lecture that these are the eigenstate of the sigma z operator, and these are the eigenstates of sigma x operator, spin operator along x direction, along the x direction, spin along z direction. So these are the eigenstate of the sigma z, these are the eigenstate of sigma x operator. So altogether we have four states here: up z, down z, up x, and down x states, and we can easily see that these four this up and down, we can easily see that this up and down, they are orthogonal to each other, but this state and this state, they are not orthogonal. Actually we can express this up x and down x in terms of superposition of this up and down z basis. So this is actually a particular basis, that is the sigma z basis, the eigenstate of sigma z operator. This up and down, they form the basis for this operator. So these are two different bases. Actually we can go from one basis to another basis, so they are related. So up x, actually we can express this up x state in terms of this z basis. So basically up x is 1 by root 2 up z plus down z, and down x can be expressed in terms of this z basis in this way: up z minus down z. Okay, so we can easily see that these states, up z and down z, they are actually they are not orthogonal to these two states. They have some. So here we can easily see that this up z and down z, they are not orthogonal to these states, because if we take the inner product between this state and this state, it will not be 0, right? So they are so we can safely say that this set of states and this set of states, they are non-orthogonal. So okay, so Alice actually prepares these particles. So what she will do, she will have many spin half particles on her possession, and she will make one by one. She will prepare she will actually prepare these qubits. She will prepare the qubits in one of these states, one of these four states. So she will prepare and then send it to Bob, okay, one by one. So she will have many spin half particles. And they are prepared in any of these four states: up z, down z, up x, down x. And these states, actually up and down z, they are the eigenstate of sigma z operator, and up x, down x, they are the eigenstate of sigma
X operator. So, and this set of state and these two states are non-orthogonal to these two states. That is very important here. So, so in the first step, Alice will prepare a series of qubits in any one of these 4 states, and she will prepare and send it to Bob one by one. So, she will prepare the particle in any of these state and then send it to Bob. So, Alice picks up spin-up particles and she randomly prepares her qubits in any one of those states I already mentioned, that is up Z, down Z, up X, or. So, these are the 4 possible states Alice actually prepares her particle or the spin-up particle in these states. So, one particular example I am taking in this way. Let us say that Alice prepares her particles one by one in these states. So, this is a particular example. So, the first particle she prepares in this state. So, she prepares her first particle in this state, for example down Z. The second particle she prepares, second spin-up particle she prepares in up Z. Next one she prepares in down X, then up Z, then up Z again. So, this she actually prepares taking a particle and randomly preparing her particle in these states. Actually among these 4 states she chooses a particular one. Okay. So, up Z, then up X, down Z, X in this way, and then what she do, then she send these qubits one by one to Bob, and then Alice send these qubits to Bob one by one. So, actually she prepared the particle in a particular state, and then within a time window she actually send the qubit to Bob. Okay, and in the next time window she will send it to Bob in this way. So, in this way actually she prepares the particle, spin-up particle in these states, and she make many particles in this way and then send one by one to Bob. So, after receiving the qubits, Bob randomly chooses a basis or observable to measure each qubit. Okay. So, for example, Alice sent this particle, and then what Bob will do, Bob after receiving that particular qubit, Bob will randomly choose a basis or observable, spin observable to measure the qubit. Okay. So, he randomly chooses spin measurement either in the z direction, that is sigma z measurement, or he will choose another spin measurement in the x direction, that is sigma x measurement. Okay. So, after receiving the qubits one by one actually, so for example, if when he receives this qubit, he will randomly chooses a basis and he will measure the spin measurement along, he will do the spin measurement along a particular direction, sigma z, either sigma z or sigma x measurement. So, for one particular case, let us say Alice sent this particle, spin-up particle prepared in this down z state, and then Bob chooses to measure sigma z. So, what will be the outcome or the measurement outcome? So, we know that this down z, this state, this is an eigenstate of sigma z measurement operator. So, he will have the outcome. So, this state is actually the eigenstate of sigma z operator. We all know that sigma z acting on this state gives us -1. This is the eigenvalue equation, right? This. So, after the measurement outcome will be -1, because this state is an eigenstate of sigma z. After the measurement, the state will remain as this will not change. Okay. Now, on the other hand, if Alice selected this measurement, sigma x measurement for this state, what will happen? Then actually we can easily see that this down z is not an eigenstate of sigma x. So, what will be the measurement outcome? The measurement outcome, to get the measurement outcome, we have to express this state as this down z, we have to express in this basis, because so when we choose this sigma x measurement, we have to express this state in the basis of sigma x, right? So, we know that sigma x basis, what are the sigma x basis? Up x and down x. These are the eigenstate of sigma x operator. So we have to express this state in terms of this basis state. So we already know that down z can be written as 1 by root 2 up x minus down x. And if we do sigma x measurement, then with probability half we will get up this state, and with probability half we will get down x, right? That is our Stern-Gerlach experiment. So in our mind there is this Stern-Gerlach picture. If Bob happens to choose this sigma x measurement for this state, then the outcome will be either up x or down x with equal probability half. Okay, and after the measurement, after this sigma x measurement, the state will also collapse to either this up x or this down x. So we summarize that in step 1, Alice prepares her particles in these states and send it to Bob, and this is the second step 2 actually. So in the second step 2, after receiving the qubits, Bob randomly chooses the measurement observable along x direction or z direction, that is sigma z and or sigma x, and he measure the qubits and he will actually record the measurement outcome. So for each qubit, so when Alice send one by one this spin half particle, Bob chooses this spin observable, right? So what Bob will then do, that is the step 3, where Bob will record his measurement basis, that is whether he is measuring sigma z or sigma x. So this measurement so Bob record his measurement basis, that is sigma z or sigma x, and also the outcome of the result, that is up or down. So that record also he actually note it down. So Bob records his measurement. So in the first step, Alice prepares her spin half particles in he prepares a series of particles in these states, and she sends this particle one by one to Bob, and after receiving the qubit, Bob randomly chooses a basis, that is either sigma z or sigma x, that is the measurement basis. And then in step 3, so I am writing it here, so that is the step 3. So in step 3, what Bob do, Bob record his measurement or the basis or measurement basis of the observable, the measurement observable he randomly chooses. So he record that measurement basis, so Bob record his measurement basis, that is either sigma z or sigma x, and also the outcome or the result of the spin measurement. So what Bob will do after receiving the particle on his side, so one particular example here I am writing. So for example, for this particle, the first particle, Bob chooses this measurement basis or measurement observable sigma z for this particle. The second particle, he chooses this sigma x. The third one, for this one, he randomly chooses this axis spin measurement direction or the spin measurement observable. Okay, sigma z, sigma x, then sigma x. For this particle or the qubit, he measures sigma z again. For this one, he measures sigma x. Okay, for this he measures sigma x again, and for this particle he measures sigma z, and for this particle he chooses or selects the spin measurement sigma z. So this is a particular example of a run of experiment. So one typical example I have taken in this way. So here, if it is the first particle was in this down, so Bob will definitely obtain again that state, right? So that we know from the eigen state, that we can definitely say, because this is an eigenstate of sigma z, so he will definitely obtain the same state and definitely obtain the outcome down state actually. So but for the second case, this is up z, this is an eigenstate of sigma z, but he has chosen sigma x measurement. So in that case, actually his measurement basis does not match with this basis. So because this basis state is a different basis states, right? This is sigma z basis state. So in that case, Bob will actually discard this case. He will not consider because they have taken a different basis. Okay, for this is sigma x basis again, and he is measuring sigma x, so he will definitely obtain this state. After measurement, he can definitely, his state will be this, and with a eigenvalue -1, so he can note it down. Okay, so for this case of z, this also matches with this basis, right? This is a basis state of sigma z, so eigenstate. So the state after the measurement, the state will remain up z, and also after doing the measurement, Bob will know that the state is this state. Okay, so after Bob measures sigma z, the measurement outcome will be +1, right? In this case it is -1. In this case they will actually discard because their basis does not match. So in this case, this is sigma z basis, but Bob chooses sigma x, so they will discard this result also, this particular case also. This is again up x, that is sigma x basis. So after Bob chooses this measurement, his measurement outcome will be this is up, right? So measurement outcome will be +1, and the state will remain, after the measurement the state will remain up x. For this case also, we see Bob chooses this observable sigma z, and here the state was sent the state Alice sent was actually eigenstate of sigma z. So the measurement, after Bob measures this particle, the measurement outcome will be -1, and the state will remain the same. And for this case, here we can see this is a basis state for sigma x, and Bob actually chooses a wrong basis, which is not an eigenstate of this is not an eigenbasis of sigma z. So in this case actually Bob chooses a wrong basis, so they will discard this result. So in the next step, that is step 4, in step 4, what Bob will do, Bob will publicly announces his basis. So he will actually announce his basis, that is for the first particle what basis he has chosen, for the second particle what basis of measurement basis he has chosen. So in this way he actually publicly announces his basis or measurement observable, that is sigma z, sigma x, sigma x, sigma z, sigma x, sigma x, sigma z, sigma z. But he does not actually announces his measurement outcomes. So that is whether he obtained this +1, -1, or +1, +1, -1, these measurement outcomes, that is up or down, he obtained that measurement outcome, he does not actually announce or disclose in public. Okay, so what he publicly announces is his basis actually. So which basis he measure after receiving the particles, so one by one. So Bob, in step 4, Bob publicly announces his basis or the measurement, whether he measures sigma z or sigma x, but not the outcome or result of his measurements. So in the next step, so after Bob publicly announces his basis or the measurement of observables, what Alice will do, Alice will check whether Bob has chosen the right basis or not. Okay, so in step 5, Alice will inform to Bob in which cases actually Bob selected the correct basis. So Alice then informs Bob in which cases Bob selected the correct basis, that is these are the correct basis, this one, okay, and these are the wrong basis, right? So these are the cases where Bob actually selected wrong basis. So this information Alice will convey to Bob by phone call or any public communication channel. Okay, so Alice informs Bob in which cases Bob selected the correct basis and in which cases Bob selected the wrong basis. They ignore or discard the result when their spin bases are different, that is these cases actually they discard these cases when Bob chooses a wrong basis. when Bob chooses a wrong basis. So after that, in the next step, that is step 6. So in step 6, Alice and Bob then use those measurement results to generate the secret key. Okay, so these measurement results they will use to generate the secret key at a distance. So one example is that they assign the bit values 0 and 1 as follows. So when their measurement outcomes are either up z, when their measurement outcomes are either up z or up x, they assign the bit values, they assign the bit value 0, and when their measurement outcomes or the measurement results are down z or down x, they assign the bit value 1. Okay, so in this way they assign the bit values. So they assign the bit value 0, and when their measurement outcomes are either down z or down x, they assign the bit value 1. So here, for example, when they obtain this down z state, they assign it as 1, down x is 1, right? Up z, when they obtain the measurement outcomes outcome as up z, they assign 0 here, and up x also 0, down z 1. So in this way they will obtain binary string, and that they will use as the secret key. Okay, and Alice and Bob both will actually, they will know that. So Alice and Bob simultaneously they will have access to this secret key. So I will write it in a more clear. So this particular typical example of key generation, so I will write this typical example of key generation in a table, and we will discuss about the security issue also. Okay, so let me write it down. So let us now summarize this quantum key distribution protocol through this table. So this is a particular case or outcomes for this quantum cryptography protocol. So Alice randomly prepares a series of qubits in any one of these states, up z, down z, up x, down x. So this is a particular case. She prepares the particles. So Alice prepares her particles or qubits in those states, like this one, down z, the first particle is prepared in this state, second one in this, third one is down x, like that. So a series of particles she prepares. There can be many actually, so I have given some, only few examples. So she prepared her particles in those states and sent these qubits to Bob one by one. So after receiving the qubits from Alice, what Bob will do, Bob randomly chooses a basis or observable to measure each qubit. So he chooses spin measurement along z direction or x direction. So for example, for this first particle, when he receives, he measures sigma z, then for next particle he measures sigma x, then sigma, for this one, third one, sigma x. So in this way he randomly chooses a measurement direction for spin measurement along z or x, and these are the measurement so these are measurement basis. For this particular case, one particular case we have shown that Bob chooses the measurement basis along these directions. So in this way, sigma z, sigma x, sigma x, sigma z, sigma x, sigma x, sigma z, sigma z, like that. Okay, so this is a particular case what Bob selected his measurement basis for this particle, that is this. After receiving the qubit from Alice, Bob chooses the spin measurement. See, he decided to measure the spin of each qubit along z direction or the x direction. So and he does it, he actually select that measurement direction randomly. So this is a particular case of his measurement basis selection. So for example, here we can see that when Alice sends this down z state, if he is measuring sigma z, so because this is an eigenstate of sigma z, so what Bob will get, Bob will actually get the same state here, and so down state the measurement outcome will be -1. Okay, so we know that sigma z acting on the down z state gives us -1 is the eigenvalue times again the same state. So this is an eigenstate of sigma z. So in this case he will actually get the same result down z. So the state will not change here because it is the eigenstate of, the state will not change after the measurement because this is the eigenstate of this operator sigma z. But here, for example, here we can see that Alice sends this up z state and Bob chooses this basis, measurement basis sigma x. But in this case actually there are two possibilities. If we recollect from Sakurai Stern-Gerlach spin measurement experiment, we recapitulate that this up state can be written as a superposition of up x and down x, or this state can be written as a superposition of the eigen basis of this operator sigma x, right? So there are both possibilities that Bob will obtain as a measurement outcome. Bob will obtain either up x or down x. Okay, so this is the measurement outcome for this sigma x measurement. So in this case they will not take this result because Bob has chosen a wrong basis. Actually this is an eigenstate of sigma z and Bob has selected this sigma x basis, so they will not consider this one, they will discard this case. So that's why I am coming to that next point. So in this way, so after receiving the particle from Alice, Bob actually measures in this way. In this case the state Alice sent was down x and Bob selected the sigma x measurement, and this is, you can easily see that this is an eigenstate of sigma x, so the state will remain the same after measurement and Bob will know that what state Alice actually sent to him. Okay, so this is the correct basis Bob has selected here. So after doing the measurement and obtaining the results or the outcome, what Bob will do next, Bob will publicly announces his basis. So after doing the measurement and obtaining the results, these results or the outcomes, what Bob will do, Bob will publicly announces his basis. So in which basis he measured the spins, he publicly announces that, but he does not declare or announces his measurement outcomes. So these outcomes he does not disclose, only this in which basis or the operator, measurement operator he measured on those particles, that basis actually he publicly announces. After knowing Bob's basis, what Alice will do, Alice then informs Bob in which cases Bob selected the correct basis and in which cases Bob selected the wrong basis. So for example, in this case Bob has selected the right basis, so he actually informed to Bob that in this case you have chosen the right basis. In this case Bob has chosen wrong basis, wrong measurement basis, so they will discard this result. In this case Bob has chosen right basis, so Alice will inform to Bob that in this case you have chosen the correct basis, so keep this outcome. In this case also Bob has chosen the correct basis. In this case Bob has chosen wrong basis, so they will discard this case. In this case Bob has chosen the right basis, so they will keep it, and in this case also Bob has chosen the right basis, so they will keep the outcome. And in this case the state was up x and the basis was sigma z, so this is wrong basis Bob has chosen, so they will not consider this outcome, so they will discard this case. So finally Alice and Bob then uses those measurement results, these results when they chooses the Bob chooses correct basis. So these measurement results, this one, this one, this one, this one, this one. Okay, so these measurements outcomes, through this measurement outcome they will actually generate the secret key. To generate the secret key, they assign the bit values in this way. So when their measurement outcomes, are this up z, either up z or up x, they assign this bit 0, and when their measurement outcomes are either down z or down x, they assign this bit value 1. So in this case the measurement outcome is down z, so they assign this bit value 1. In this case the measurement outcome is down x, so down x means they assign the bit value 1 here again. Here the measurement outcome is up z. If there is up z, then they assign the bit value 0 here, and for up x also 0, for down z 1. Okay, in this way they will obtain this simultaneously. They will generate this secret key like 11001. There will be long bit string. They will send actually many more particles, and then they can generate simultaneously this raw key or the secret key simultaneously, even if they are at a distance. So they can generate this secret key simultaneously. So even Alice and Bob are at a distance, they can actually generate this secret key. Alice and Bob, they both will have access to this secret key even they are at a distance. Okay, so this is a particular case we have actually demonstrated here for BBAT4 protocol. If no hacking or eavesdropping has occurred, I mean any intruder in the middle between Alice and Bob, if they have not hacked or tried to eavesdrop or tried to know the spin state of the particle, if there is no hacking or eavesdropping between Alice and Bob in the middle, then all the qubits measured by Bob in the correct basis like that should match the spin state originally prepared by Alice. So what I am saying is that if Bob has chosen the correct basis, then the state sent by Alice should match with the. So if no hacking or eavesdropping has occurred between Alice and Bob in the middle somewhere, then all the qubits measured by Bob in the correct basis should match the spin state originally prepared by Alice, because they are the eigenstate, right? For example, this case, Bob chooses this sigma z, and Alice sent this state which is the eigenstate of this sigma z. So here actually Bob's measurement outcome should match with this original state of Alice. So that is the point. Hence Alice and Bob can use this spin data as their raw key for the secret key generation. However, before they proceed any further, they should sacrifice a small number of those qubits to test for eavesdropping. For instance, they can do the following. So Alice and Bob randomly select a fixed number of qubits, for example this third qubit, in which case Bob has selected the right basis. Okay, Alice and Bob randomly select a fixed number of qubits, say for example this nth qubit here, for example this one, third one. Okay, so they have chosen, Bob has chosen the right basis, so their measurement outcome and Alice's original state, they should match, right? So they will actually declare through public channel or public, they will declare their, so Bob will, in some cases Bob will declare the outcomes also, and he compare with Alice whether the measurement outcome is matching with Alice's original state. So what Bob will do, Alice and Bob will randomly Alice and Bob randomly select a fixed number of qubits, for example in this case third, or maybe this one, and Bob will actually publicly announce the measurement outcome also, and then Alice and Bob, they will compare the result, whether they will check whether the measurement outcome of Bob matches with the original state sent by Alice in this case, because in this case Bob has selected the correct basis. So if they detect that they do not match, then there is something wrong, that is some eavesdropping has happened or some wrong thing has happened, right? So if they detect a significant mismatch indicating a high error, they conclude that either substantial eavesdropping has occurred or the quantum channel is unexpectedly noisy. So consequently, because the expectation is that their results should match here because Bob has selected the correct basis, but if the measurement outcome does not match with the original state of Alice, then actually in the middle between Alice and Bob, someone has tried to know the state of the particle, so they will immediately know that something is wrong. So consequently, Alice and Bob should discard all this data and start with a fresh batch of qubits like this, what they have done here. The security of this BBAT4 protocol is guaranteed by the principle of quantum mechanics, specifically the no cloning theorem and the uncertainty principle. An eavesdropper or a third party cannot gain information about the state of the qubits without performing the measurement, right? Cannot gain the information about the state of the qubits without performing measurement, which inherently disturbs the system. and if a third party attempts to do the spin measurement in one of these bases sigma z or sigma x, they can be detected when Alice and Bob compare their result, subset of results. In some in particular cases they actually they will compare their Alice and Bob will compare a subset of their results, and through this matching or mismatching they will know that someone has tried to actually eavesdrop their data. So they will actually then they will be alert. So they will be alert before sending the message. So they will not send the message with the same secret key. They will again actually start to generate the key again with a proper precaution. And here this no cloning theorem all further ensures the security, as the eavesdropper cannot copy these non-orthogonal states. So because this up z, down z, up x, down x, they are one set of states are non-orthogonal to another set. So the what no cloning theorem says that you cannot copy non-orthogonal states, right? So this no cloning theorem, the no cloning theorem in quantum mechanics further ensures the security of this BB84 protocol, as the eavesdropper cannot copy non-orthogonal states. If copying were possible, the eavesdropper could determine the state through the measurement statistics. So what eavesdropper will do, he could actually, he or she could actually copy those states, make many copies of the states, and then they will measure, and through this repeated measurement they will obtain a statistics, and from that statistics actually they can determine the state also. So that is not possible because non-orthogonal states. So that is not possible because of this no cloning theorem, that non-orthogonal states cannot be copied. In this case they are linearly dependent. Okay, so if copying were possible, the eavesdropper could determine the state through this measurement statistics. We note that this BB84 protocol is not the only quantum key distribution protocol. There are other QKD protocols also, namely Bennett 92 protocol, other variations of BB84 protocols, entanglement based Eckart's protocol, and this subject is actually quantum cryptography is a vast subject, and still research is going on, and there are several technical issues also, and so I hope that I will be able to discuss more on those issues. And so this one is a very basic lecture on quantum cryptography, but to know more about the subject one has to go through the recent literature. There are many review articles, there are books, so one can easily go through the current development, what is going on in this field, and I hope I will be able to discuss with you more in the near future. Thanks for watching. Please don't forget to subscribe the channel and tap the bell icon to get notified for my new lecture videos. Please comment below. Your thoughts and suggestions would be greatly appreciated.